I thought we could just spend today answering questions. You could work on some problems yourselves before we go on to the next topics. Just make sure everybody's making sense out of this stuff. So first, anybody have any questions on homework problems or topics? Yep.
Yeah, I am also with the homework. I noticed that it seemed like it was assigned like this problem here, this problem there. I just been kind of jumping on in and did the whole damn thing.
Oh yeah, okay. Yeah.
So I got to be careful with that.
Okay. Well, you got it. They're going to be assigned anyway, so when you do them, I guess doesn't. Okay. You can do it like that.
So eventually they're all going to be.
Yeah, that's right. Okay. Yep. Any other questions? Okay. Anyone have it with them? Yeah, I know, that's true. Where is she? Erin. Oh, okay, that's right. Huh. Yeah, it's sad. Number 2 in strain, right? Oh, in principal stresses. Okay, yes. Over there. Okay. We're supposed to use the Okay, so it's the material in number 1. Anyone know what the? Well, let's do it all. Start at the beginning. Are you planning to take notes on that or something? Is it all right if I use it for a second? Okay, let me just write it down. So, okay. Okay, so first, we're given this tensile test. This length is originally 0.25 meters. And this is 0.1. And the thickness is 0.005. And then it's put into tension, and after the deformation, the length, so I'll use this coordinate system. I'll call the up-down axis X, Y, and then Z coming towards us. And after the deformation, the length along the line axis is 0.25022. And along the Z-axis is 0.09. There's 3 9s and then an 8. And the force applied is 8,000 newtons. And we want to calculate Young's modulus and Poisson's ratio. Young's modulus is the stress along the loaded axis, that's X in this case, divided by the strain along the loaded axis. And the Poisson's ratio is the negative strain in one of the off axes. We're going to use the Z because that's the measurement that we're given, divided by the strain along the loaded axis. And so we need to figure out three things: the XX stress, the XX strain, and the ZZ strain. The XX stress is the force divided by the cross-sectional area. You can think of that as the cross-sectional area that is resisting that force. So we're just talking about like that area there. 0.1 times 0.005. Yeah, okay, so in this whole class, when we talk about an area or a volume or whatever, we're always going to use the original one because we're assuming such small deformations that it's just not worth the trouble of using the deformed. It would be just a tiny fraction of difference, you know? And so, yeah, we're going to use the original. So 8,000 divided by 0.1 divided by 0.005. And what do you get for that? What? 1.6 times 10 to the 7 pascals. And then the strain in the x direction is going to be, that's the change in length divided by the original length. So that's 0.25022 minus 0.25 divided by 0.25. And what do you get for that? 8.8 times 10 to the negative 4. And then the strain in the z direction is the deformed length along that axis. So that's 0.099980 minus the original length divided by the original length. And what do you get for that? Okay. And so the Young's modulus for this material is 1.6 times 10 to the 7 divided by 8.8 times 10 to the minus 4. And what do you get for that? .82 times 10 to the 10th pascals. Or that's 18.2 gigapascals. And then the Poisson's ratio is negative of negative 2 times 10 to the minus 4 divided by 8.8 times 10 to the minus 4. And what do you get there? 0.23. And so now for this material, so this material's constitutive relationship is defined by, if you have that compliance matrix function, you just do compliance type in 1.82 times 10 to the 10 and 0.23, and it'll spit out this matrix that's 1 over e, where e is this value, negative nu over e, negative nu over e, 0, 0, 0, and give you that big 6 by 6 matrix. Okay, so now number 2, it says to use the material properties from number 1. So we're going to use this compliance matrix here for all the questions where we have to go back and forth between stress and strain. Okay, so now suppose that the stress tensor at a point is negative 20, 0, 0, 0, 0.4523, 2.5652, 0, 2.5652, negative 14.5477. And this is in megapascals, so if you wanted that in pascals, it would be all of this times 10 to the 6. And we're supposed to find the strain. We're supposed to find the principal stresses. These are really all just about the principal stresses and the principal axes. The axes of the principal coordinate system. Yes. No, the eigenvectors are the axes. That's right. And remember that the eigenvectors that you get, so say you get the eigenvector 1, 0, 0. Okay, that means 1, 0, 0 works and negative 1, 0, 0 works. So you're going to have to change the direction of those axes to make it an acceptable coordinate system. You can't have the x-axis crossed with the y-axis give you the negative z-axis. And so you might have to switch the direction of one of those axes to make it work. And then D, what's the strain in the new principal coordinate system? And the last one is to give the stress tensor, give a stress tensor that contains the maximum shear stress. Okay, so first for A, can someone punch in that E and Poisson's ratio and give me the compliance matrix that you get? Yeah, just the numbers. Okay. Negative 11, okay. Yep. Okay. Okay, and then let me fill in all these. Okay, and then what's that shear coefficient? Okay. Okay, so that is all we need to go from stress to strain. Or if we want to go from strain to stress, we need the inverse of that. And so the Voigt stress is the XX stress, YY stress, ZZ stress, yep, that's right. And then we have YZ, and then XZ, and then XY. And all of these are times 10 to the 6 pascals. So then the strain, the Voigt strain, is the compliance matrix times the Voigt stress. Can someone calculate that? So you're just going to multiply that compliance matrix to this vector. Yep. Oh, negative. Okay. 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 3.467 10 to the minus 4, and then zeros. Anybody having any trouble doing this calculation? Just finding that compliance matrix, multiplying it by the Voigt stress. Any questions about that? Okay, and then for part B, this is B and C are all the principal stress stuff. So if you have a calculator or a computer that does it, you're just going to do some version of running this program, eigenval, where the argument is just that original matrix. Zero, 2.5652, and then negative 14.5477. And it gives you these values. Let's see. So negative 20. I think we probably have a negative 14.9 something, right? I'm just kidding. I just did that today. I just happen to remember that one. I don't know how to do that in my head. And then what's the other one? Okay. And those are all megapascals. And then run some version of this program eigenvector on that same matrix. And it gives you vectors corresponding to these three values. The one corresponding to the negative 20. What's that vector? Yep, that one I could have done in my head. These two are harder. What's the second one? Okay. 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 986, negative 0.164. Okay. So now you can make any coordinate system you want out of these three vectors or their negatives. It has to be an acceptable coordinate system. And once you've chosen that coordinate system, you just have to, in your principal stress tensor, your principal stress tensor is only going to have non-zero values along the diagonal, and they're going to be in the positions according to what you made your axes. So I'm going to do it like this. I'm going to say the principal stress tensor is, I'm just going to put them right in order, negative 20, negative 14.97, 0.879. And that means that 1, 0, 0, or its negative is going to be my new x-axis. My new y-axis is going to be this one or its negative. My new z-axis is going to be this one or its negative. So basically what we have is, so if I'm going to draw this coordinate system, our new x-axis is still where the old x-axis was. Our new y-axis is in the negative z direction. So that's, I mean, not exactly, but basically, you know, it's pretty close to exactly in the negative z direction. What? Yes. Thank you. And then my new z-axis is basically in my negative y direction. So this way. Okay, so if this is the coordinate system you choose, then this is the principal stress tensor. This is the stress tensor in that coordinate system. If you chose a different one where this was x, this was y, and z was coming out, then it would still be these values. They'd just be moved around to reflect where the, you know, yes?
Is z backwards? Does z have to go up?
Probably. X.
Oh,
Oh yeah, right. Well, so yes, I drew it the way that this vector says it, and then if you do the right-hand rule test to make sure it's an acceptable coordinate system, that says this isn't allowed. And so, yep, you're exactly right. This has to be this way. We're not going to like do a ton of that kind of stuff, but yes, you're exactly right.
So,
Yes, those three eigenvectors are always going to be perpendicular. Why is what? How did I find those directions?
Oh no, like coordinate.
So these eigenvectors are given as components of vectors in like your original coordinate system. So let's say this is our original coordinate system, okay? And then the components of those eigenvectors tell us what direction the new axes are. Okay. Mm-hmm.
I don't get
Okay. Okay, well, since I put the negative 20 in the x spot, that first eigenvector has to be our new x-axis. And if you draw a vector, if you draw this vector in this coordinate system, it's just aligned with the old x-axis. So that's the new x-axis. And then the y-axis, I made negative 14.97 the y normal stress. And so that means that this, or its negative, has to be the new y-axis. And that's basically just, it's not quite in the direction of the old z, negative z-axis, but pretty close, you know. This is pretty close to 0, this is pretty close to negative 1. So really it's a little bit in the, it's really a little bit in the positive y direction, and mostly in the negative z direction from the old axis. And then this one is mostly in the negative y direction, a little bit in the negative z direction. So I just drew them aligned with the axes because it's pretty close to being aligned, but it's off by, I don't know what the inverse cosine of 0.986 is, but it's around 10 degrees somewhere. You know, so it's pretty close to aligned with this, just rotated 10 degrees.
Could be just up and into the board like a little bit, kind of.
Yes, that's right. Yep. Now you don't have to make this the x element and the y element and the z element. You could, if you wanted to, say like, well, doesn't it make more intuitive sense to make the new x-axis basically go that way, the new y-axis basically go that way, and the new z basically go that way? You could do that. They'd be off by about 10 degrees, but you know, there's something nice about having those coordinate systems as close as possible to each other so you can compare stuff. Well, then what you would have to do is your x-axis would be this, your y-axis would be negative this, your z-axis would be negative this, and then your elements would be negative 20, 0.879, negative 14.97. So you have all these, there's a whole bunch of choices of coordinate system. This is just one of them. All of the acceptable coordinate systems have a face that's perpendicular to this, a face that's perpendicular to this, and a face that's perpendicular to this, but you have a whole bunch of choices.
100 next one is like x is 1, so going from that.
Right.
Negative 14, 0, and the z-axis is negative 1, so it's going to the negative z-axis.
Yep.
And the 0.879, why is it going?
Because that's basically in the negative y direction.
Oh, okay.
You know, it's almost, this is a unit vector, so
yeah.
So no element can be bigger than 1.
Yes.
But this is almost negative 1 here, right? This is almost 0. So that's pretty close to the same direction as 0, negative 1, 0, which is our old y direction.
Oh.
Well, it's our old negative y direction, but you can take the plus or the minus. Okay, well, so the only reason in this class we don't have any need for knowing these, the orientations of this new coordinate system, but I just want to spend a little time with you thinking about this stuff because it's important information that's sometimes useful. We're just not going to use it for any calculations in this class. Any other questions about that? Okay, and then, so that's B and C. And then the strain. So part D is to calculate the strain in that new coordinate system. So the strain is just equal to that same original compliance matrix times the principal stress in Voigt form. I don't know, I guess I'll write it like that. So in Voigt form, the principal stress is 20, negative 14.97, 0.879, and then 0, 0, 0. Yes. And so the Voigt form of any principal stress has zeros in all the shear elements. The last three elements are 0. Can someone calculate that? Can someone calculate the normal strains, and I'll calculate the shear strains in my head? 208. Okay. 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 Then 0, 0, 0. Yes. Still got it. So since the normal strains, since the shear strains only depend on the shear stresses, and you know that the principal stress doesn't have any shear stresses, the strain in the principal coordinate system also has to have no shears, which means that if you look at a cube that's originally aligned with the principal coordinate system, its deformed state is going to be changes in length, but no angle changes. Okay, so that strain in the principal coordinate system, none of the angles between the sides change. It's still a rectangular solid. It's not even a parallelepiped, can be all skewed and stuff. This thing will still be a rectangular solid, I guess is what it is. Yeah. Whereas, in the original coordinate system, we calculated that strain, and we only had one non-zero shear strain. But so in that original coordinate system, if you started with a stress cube, after the deformation, it does have angle changes. But a cube aligned with that principal coordinate system is going to stay rectangular. And then the last question was, okay, so now we want to find the stress tensor that contains the maximum shear stress. And the way to do that is, so remember the principal stresses, there's two important ones. There's one useless one, but that useless one is aligned with an axis. And to get the max shear stress, you rotate your coordinate system about that useless axis. Okay, so for our principal stress, which one of these is the useless one? The negative 14.97 is the one that doesn't mean anything to us. In our coordinate system, what axis is that corresponding to? Well, in our new coordinate system, it corresponds to the y-axis. Like in the principal stress tensor, it's in the y position. And so we're going to rotate this coordinate system 45 degrees about the y-axis.
With vector form, because
yeah, but we're rotating it about that rotation matrix. So this tensor is in this coordinate system. Okay? And so we're going to do our rotation based on this coordinate system, not on this one. And in this coordinate system, negative 14.97 lines up with y, because it's just in the y position. Okay, so that middle eigenvalue is in the y position. And so the rotation matrix Q is equal to 0.7071, 0, negative 0.7071, 0, 1, 0, 0.7071, 0, 0.7071. And the stress tensor containing the max shear is equal to Q times the principal stress tensor times Q transpose. And can someone calculate that? Okay. Times 10 to the, this is megapascals? Okay. And then 0? Okay. 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 Zero. I rounded for no reason. Okay. So this is megapascals. And so what that says is that the maximum absolute value of shear stress is 10.4395. Okay, so now let's so now you can also calculate just the value of the max shear stress, tau max, as the maximum principal stress. That's the one that's, so of these, what's the maximum principal stress? 0.879. Minus the minimum divided by 2. And it might not match exactly because of round off or whatever, but you can see it's pretty close. It's going to be 10.440 or something. It works.
So, which one we got 10.4 for other?
Yeah, so just using the simple formula where we didn't do any rotations or anything, we just take the maximum principal stress minus the minimum principal stress divided by 2, and we get 10.44. And going through all the rotations and stuff, we found 10.44 also.
But one of them
For the maximum shear stress, all we care about is the absolute value.
Oh,
yep. And you also, by the way, you could get the same thing rotating negative 45 degrees about the y-axis. I think in that case, some of the signs would change. I don't know off the top of my head which ones. But then in that case, you might get positive 10. But all you care about is the absolute value. And then you'd compare that maximum shear stress, 10.44, to the maximum allowable shear force for your material, steel or whatever material you're working with, to see whether you're in a range where you're concerned about this thing breaking or going into the plastic range, permanent deformation, that kind of thing. You have another question? Okay. Anyone else have questions about this problem? On the principal stresses? Not this assignment, the assignment before?
Yeah, I got it here.
I have it here. on my new computer.
You know,
Yeah, new to me.
I replaced the hard drive and the RAM. Upgraded. The CD-ROM is working more.
Oh, really?
I was doing a thing where like I just randomly started like trying to download
Kind of read something.
So I just like
We did that one? I don't really remember. Okay. Okay. Oh. So yeah, if there's any notes that you want that I know there was a class or two that I missed. Sorry about that. What you need to do is just look on D2L. There's a section called Old Lecture Notes, and you have to just look through there until you find the right topic, you know? And the lecture will be pretty similar, using most of the same examples and stuff. And same thing on YouTube. There's a playlist on YouTube that's called D-Forum Spring of 2016. And once you find the lecture notes, then you can just go to the corresponding lecture video. But I already deleted the raw files. So yeah, because I thought I'd already made the videos and stuff, so I can't get them now. Any other questions? The first one took an hour, so I'm sure I can answer the next one in 4 minutes.
so if you did the string tensor shear stress in it. Before when it was just the principal stress, I only had values for the normal strains.
Yes.
So with
Yeah, that's a great
this
question.
other one,
Is it only going to have angle changes?
yeah, where is it going to have one shear?
It's only going to have as many, it's only going to have the shear values that it has shear stress values. Because the shear strain only depends on the corresponding shear stress. So like in this case, you know, we only have in this maximum shear tensor, we only have a non-zero shear strain in the XZ position. So there's only going to be an XZ shear strain. There is going to also be, because we have normal stresses, there's going to be normal strains. And there is such a thing as a stress tensor where all you have is shear stresses. But, you know, I said that every stress tensor corresponds, you can find a coordinate system where you only have normal stresses. That's not true for shear stresses. It's only a rare case where there's a way to rotate the coordinate system to come up with a stress tensor with only shear stresses. It's called pure shear, and it's yeah, it's not always possible to find that. But in pure shear, all you have is angle changes, and all the lengths stay the same.
Normal stress and solenoid shear stress?
No, it's so if you had a, I mean, this is an example of pure shear. So if this is your stress cube, if you had like that, and all that's doing is, let me draw it in a way that's where I can draw what it would do physically. So let's say you have that, and then you have corresponding ones down the back, and this way on the bottom. What that would do to this shape is deform it like this. You know, it's like if this is your hand, you're pushing this way, and this is your other hand, and you're pushing this way. You need thumbs. No. If you take a, so if I take this box and do this, that's pure shear.
Oh, okay.
Any other questions? Yep.
Back when you got the new principal stress,
Mm-hmm.
and then you switched it to you know, you got that XX by line.
Up here.
Yes. So when I did it,
Mm-hmm.
principal stress,
Mm-hmm.
I had the negative 14.97.
Okay.
And then it was like also the one I did the middle one was off. But I still got all the same values.
Yeah. So if you put, say you put the 14.97 here, and the negative 20 here, and this here, that just means that when you think about the coordinate system, so now your XX element is negative 14.97. So your new x-axis has to be parallel to this. You know, this one's corresponding eigenvector. And now your negative 20 is in the y position. So your y-axis has to be parallel to the eigenvector for the negative 20. Okay. All right. Great.